Hey, man, PCP land.
Welcome back.
Thank you. Parallel computing platform land.
Thank you.
But you know, we've been saying that so much in these videos that I think it's no longer an issue.
Yeah, we're no longer druggies. We're actually focused
Absolutely
on.
not. So introduce yourself.
So my name's Stephen Toub. I'm a lead program manager on the Parallel Computing Platform team. And I'm here with folks from both our managed and native development teams.
And people who've been on before.
Exactly.
Dana.
I'm Dana Groff. I'm a senior program manager, working on a couple different things. Transactional memory we talked about before. And
Yep.
I'm also working on the concurrency runtime in C++ as well.
Outstanding.
And I'm Rick Molloy,
Hey.
a program manager, and I spend most of my time working on the Parallel Pattern Library and our C++ programming models.
Excellent.
And I'm Don McCrady. Hi again. I'm the development lead for the concurrency runtime team, so I spend a lot of time thinking about many of the things that Rick does in addition to the underlying scheduler engine that runs all our concurrency programming models.
Excellent. So let's talk about this. I mean, when we first were thinking about this, and I think we had a conversation with you at PDC about this conversation, or maybe that was another conversation, but either way, we've been covering a lot of stuff on parallelism on Channel 9. You can thank to your team. And there certainly is the managed approach and then the native approach. And then, of course, native runs it all way under the covers. Let's talk a little bit about the different approaches you guys take when you think about coming up with solutions. Because you know you're targeting .NET developers on one hand and then systems types on the other. Is there a different...
Right, so there's certainly lots of things that impact how we design the APIs and the runtime for both managed and native. There are lots of similarities and there are differences, and the differences, a lot of them stem from, I think, predominantly two factors. One of which what the platform, what the system actually provides. So from the native perspective, what C++, what you have at sort of the raw OS level, and with .NET, what the CLR provides and what the .NET framework provides. And then there's also expectations from the sort of the second thing is expectations from developers. So what do developers coming to C++ expect from their programming models? What do .NET developers, C#, Visual Basic, F#, whatever it may be, what do they expect from the programming models? And that includes things like patterns they're familiar working with. What does it mean for someone to approach parallelism who's familiar using enumerables versus someone who's used to using iterators? You know, the .NET framework design guidelines for how you develop types versus sort of the standard design guidelines that you have with typical C++ applications, STL versus .NET framework, and so forth. So there are sort of lots of factors that go into how we go about designing these APIs to both meet the needs of the developers and also their expectations for how they can easily work with these APIs when they sit down with them for the first time.
Excellent.
I think the hope is that if you sit down with either of these APIs, that the concepts translate really well back and forth, and that the programming model feels like the programming model that you're working in, so that's familiar too. And whether you're calling task.factory.startNew or taskscript.run, it's not that big of a deal. But the way that you actually declare and create tasks is incredibly similar, and the things you think about when you're doing that are the same things. And we hope that is the thing that actually shines through and is consistent.
And the concepts, I think, sort of the higher level point is the concepts are very much the same, whether you're using our managed APIs or our native APIs. When you're dealing with tasks, when you're dealing with groupings for tasks, when you're dealing with a scheduling entity, when you're dealing with the concepts of data being passed around in some fashion. A lot of it translates whether you're using native or managed. The actual way that it manifests through the APIs ends up looking different.
Sure.
And a lot of that's on purpose. I won't say 100% of it's on purpose, because it never ends up being that way in a development project, but most of it is. And if you look at the folks that are working, we're all part of the Parallel Computing Platform team. We all report up to the same folks. But if you look at the developers and the testers and the program managers that are on the managed project versus those that are on the native project, a lot of the folks on the native project have been using native APIs and native development environments for a very long time. And if you look at the folks on managed, the same, but for managed. And so they come to these the design meetings, they come to the sessions where they're figuring out what these things should do and how they should work with that model as the customer of that particular platform, and they're able to then influence the designs in different ways based on that experience.
No, okay.
I'm going to also interject. We do have some customers that are demanding different things. So particularly in the native space, we have customers who are layering their own parallel libraries on top of our concurrency runtime, which is a little different than in the managed environment. So I say not just are we talking about the environment and the preconceptions that we bring to the table, we also do have different customers. And we have, we're taking those customer requirements and providing them the APIs and the knobs and the buttons that they're asking for. And then, and not only does it because I think it's the environment, but also because of the customer demand, there might be a little more finer grained control, let's say, in C++ than there is in C#, where you might not have so many different APIs that you could then layer on. There's fewer layers, I want to say.
The goals,
in that environment.
I think the goals end up being different, which then impacts where we make investments. So if you assume we all have the same amount of time to get our solutions out for both managed and native, we end up investing more on the native side in the platform for the very reasons that Dana mentioned. There are other folks that are going to be building on top of the lower level runtime, so we invest more in the runtime. And we still have a nice API layer, but there was more investment in the runtime. Whereas on the managed side, where we took some aspect of that runtime work and built it into the thread pool, but a lot of that was being done by the CLR team, we're then able to make more investment in the API level. And so you sort of have a little bit of an imbalance in terms of where we're spending all of our efforts between managed and native.
And of course, the CLR team is a team of a bunch of native developers because the CLR is written in C and C++. Is there any thinking about them using like the concurrency runtime in the CLR? No comment. We can't talk about that. I'm sorry. That's okay. I just want to bring it up.
We can say that yes, there has been some thinking about that.
Okay, cool, fine. I mean, it's not rocket science, but I was just saying that's one of your customers. I thought that was kind of an interesting approach for today's conversation, was sort of the customers that you guys approach as well. Not just the concurrency problem, but C++ developer is different than a .NET developer. Period. They have different ways they approach the same exact problems because of the environment that they use.
Yeah, but I wouldn't overstate those differences. I really think those differences are superficial and just show themselves up in the syntax of programming model itself. From a very high level, we have quite a bit of parity in terms of the solutions to problems that people trying to inject parallelism into the program are going to run into. We have loops that don't have dependencies that we can parallelize. Well, we have the same solution, just with different names and different syntax and different stylistic biases. But it's the same high-level solution. It's the same problem that they're trying to solve. There's very little difference in terms of the actual problems that one platform can solve versus the other platform. So I don't think your parallelism needs are going to drive that decision one way or another. You're going to choose the .NET platform for other reasons and use TPL or P-Link to inject parallelism into it, or you're going to decide you need a native solution and use the concurrency runtime to get parallelism in it.
And I think Don brings up a very good example of that of P-Link, right? So we already have Link in the managed stack.
Yes.
And it would be a shame. We have this beautiful model that allows us to say what we want done rather than how we want it done. It would be a shame not to take advantage of that for parallelism, and we have. And so we've invested a lot of effort there on the managed side to be able to parallelize P-Link with just that as parallel, or parallelize Link with just that as parallel. On the native side, we have no link, right? It just doesn't exist. And so investing in a P-Link-like model would first require investing in sort of a new sequential model that we could then potentially parallelize. So we sort of bypass that, and we come up with something like asynchronous agents, which is sort of the new model we have in native.
Yeah.
We've invested a lot of effort there for this release in being able to create these nice data flow abstractions for message passing and pipelines and so forth.
It's interesting you bring that up, because I was just talking with Dana yesterday about a link query that you were parallelizing, and I had done something similar in native. I'm like, wow, his looks really pretty. Mine has a lot more code. I'm like, oh, right, it's Link. But with agent, and I did mine actually with agents, and a little bit of tasks, but mostly with agents. With agents, again, you'll see similar, as we talked to here on Channel 9, we talked about Maestro. And all of the concepts in Maestro, most of them, not all of them, but a lot of them are actually there in agents. and some of them are named incredibly similar. The syntax is different, but the actual, the guidance and the guidelines and the concepts are absolutely there. And so even here in this space, which is not task parallelism, we have some similarities, and we're trying to help people think about things in the same ways, regardless of the platform you're building on. And I think that's important, right? Because you should be able to work in the environment that's important to you, based on your project, and be productive.
Now, of course, there do end up being differences in the platforms, right? There are things that we have on managed that we can take advantage of on the managed side, and there are areas in native where things are super fast and we don't have the luxury of that on the managed side. And those do end up sort of planting seeds of differences in sort of the different implementations. And it's amazing how fast those seeds can grow as they sort of blossom through the APIs and create things that, yeah, we can do that here or we can't, and because we couldn't do that, well, now we have to do this, and so forth. And those do end up manifesting. Things like garbage collection on the managed side, we can rely on the fact that we don't have to track references, and as a result, we can sort of have these objects that have this rich functionality. We can sort of rely will just go away at some point in the future. We don't have to worry about it. Where on the native side, if we had to kind of track all that kind of information, it would really weigh down the system. You see this with things like parent-child relationships between tasks on the managed side. We do have this very tight coupling where a task is able to track its parent. On the native side, if we had to sort of maintain that lifetime information, that would add a lot of weight to the system. And thus we do have this sort of relationship between task groups instead of tasks, and it becomes a much lighter weight and more performant implementation for native.
Interesting.
The other way that ends up manifesting itself is in managed, you'll in the parallel extensions library, for example, you'll find a lot more concurrent data structures because you can do a lot more concurrent lock-free data structures when you have a garbage collector managing your lifetimes. Whereas in the native space, it's actually really difficult. There are a lot of incorrect lock-free queues out there, because they don't deal with lifetime issues and the ABA problem that you get when you delete something and it gets reallocated in the same spot, and an interlock pair suddenly succeeds when it should have failed. Those things just don't happen on managed. So in that sense, managed does benefit from this garbage collector. Now on the flip side, Stephen alluded to, on native we benefit a lot from just having a stack that we can declare things on very quickly and avoid allocations altogether in strictly structured parallel cases, and get a lot of performance boost from that. And a lot of our parallel algorithms, our parallel for and iterating algorithms, are all based on this kind of stack optimization that we take advantage of.
Yeah, well, the other thing about the allocations is that from a native customer perspective, when we talk to customers, one of the things that they've told us is that they want to have a lot of control over the allocations because it's their allocation. And so we have more flexibility here. And that's just, it's just a side effect of, I think, the environment. It's not, there's no, I think, subjectivity to it, it just is.
And along the same lines, there are some things we've had to spend time building in our native solutions that we've sort of gotten for free with managed. So you look at, again, the GC, which not only provides collection services, but also impacts how things are allocated. Excuse me. Also impacts how things are allocated, and it can do so in efficient ways. It knows if you're, it expects you to be allocating for multiple threads, and it can, with using certain flavors of the GC, account for that and provide additional efficiencies there, such if you're using the server GC. Whereas on the native side, we have to kind of go and build that ourselves and build an efficient caching suballocator and so forth. And so we've had to make additional platform investments where the CLR team and .NET has provided a lot of that for us.
Well, I mean, it brings up a good point. I mean, I interviewed Patrick, I don't know, a couple of years ago, and one of the things he said, I mean, the CLR will be synchronous sometimes when it does, the GC, when it does a global collect, right? All of a sudden, everything stops for a brief period of time. If you're dealing with 1,000 cores and some massive computation, that sucks.
Yeah.
So he still has work to do. I wouldn't say that the CLR is 100%.
Oh, it's certainly not, and I'm not implying that.
No, you're not. I just got to throw that out there.
Absolutely.
I mean, you guys are agreeing too much, so I was hoping there'd be some warfare.
Tension.
I'm just kidding. Well,
Did you catch that?
Yeah, it's on camera. HR violation.
Oh, and the
Channel 9 is an H-sharp violation. No, I'm playing.
well, and the heap can be a contention point too in native, right? If you're going to pound on it, it's going to be pounded on, and if it shows up, it's slow.
Mhm.
I mean, you just have to be cognizant of that, whether you're in managed or in native.
Sure.
I mean, it doesn't go away.
But so let me ask a question though. From the native side, like for one of the patterns that the managed code world is taking is decorating code with hints that to the JIT and the compiler that this can be run in parallel. It doesn't seem to be that simple in native code because a lot of times part of your algorithm is dealing with like a really complicated memory issue. In other words, you have more things up front that you can screw up. So what I'm thinking about is like, are you guys thinking about moving the native languages to a similar kind of pattern where you just instruct, like I don't know what the right type, decorate your code,
Annotate.
declarative, annotation, you got it.
That's definitely a forward-looking goal we have. So when it comes right down to it, the .NET languages are more set up for that than the native languages. They have attributes already, so that any user can inject a metadata or annotations on classes, functions, etc. So at least there's platform support for that. In native, it's not such an easy thing to do. You have to change the language themselves, and for a language like C++, you really don't want to introduce vendor-specific extensions to do that. So you have to go through a standardization process and get buy-off there before anything like that happens.
And there is some work.
Sure.
I mean, because we're doing some annotation already in Visual Studio, and there's some work in the language itself in C++ OS with concepts, but it's still really, really new. And I think just like when templates have been around for a while in C++, it kind of took a while to move towards, I think, the current generic programming that people do with templates. It took several years before people really got it. I think that, or I'm hopeful that in the future, after concepts have been around for a while, and we've played with them and they've been refined and fixed a little bit if there's issues with them. We don't know because no one has any implementation that works, that we'll get some forward progress in this, but we still have some fundamental difficulties where the native environment, because of its composability and because of the library you call it, just isn't set up in the same way that that the CLR is for this kind of annotation and decoration. It's just not that easy.
Isn't it? And I mean, is it fair to also say that it's unsafe, right? I mean, isolation needs to be kind of part of any durable solution. So when you have sort of an environment where you can scribble over anyone else's memory, you can do pretty much whatever the hell you want. There's no guarantee of type safety. You get that in C# when you don't use unsafe. So what kind of, that's what I mean.
To some extent, right? But
to some
you
extent,
could end up sharing object that you didn't mean to share, and you're sharing in the same app domain, and you may think you have exclusive access to it, but you don't, and someone else may think the same thing, but they're wrong as well, and you end up scribbling on the same memory. It's not necessarily just pointers that get you into trouble. You can also get into trouble by accidentally having a reference to something that you shouldn't have had a reference to.
Shared memory, but it's never going away.
It's never going away.
It can't go away. It would be useless. I mean, it can't go away in the near future.
Yeah, and it's not even anything different between native and managed. That's one thing that is universally shared pain point. You're parallelizing anything, you have to worry about shared state, and you have to worry about no matter what platform you code to.
Well, you just use Erlang, man.
Do that. Well, what we are trying to do is give you the tools to not only manage your shared state, but to eliminate shared state. And and so some of the templates that we're providing in the native environment, particularly agents, and the message passing, and very lightweight agents, so it just becomes natural to express your algorithms in ways where you're not sharing state, particularly across multiple threads. And I would say the same is true when you start using p-link. And so instead of necessarily looking at annotations as a solution where we're hoping the compiler catches us before we do something wrong, let's instead provide the tools and the patterns so that you write it correctly in the first place. And and now this is where guidance and kind of the encouragement of writing the program correctly the first time as opposed to having the tools help you find out where you wrote it incorrectly, really comes in. And in fact, Rick and I were just talking to a customer who works in academia, and he was very optimistic that he can take care of a lot of problems just through education. Maybe more optimistic than we are, but on the other hand,
I hope he's right.
I hope he's absolutely right that if really you start expressing your problem in ways that minimize shared state and maximize the scalability of that problem, then all these tools that we need, and the thing I'm even working on in transactional memory, becomes unnecessary because I don't have shared state. Okay, I don't have that unsafe pattern. I've already expressed it in a way that is just naturally scalable. And if people start thinking that way,
Agreed.
and the tools allow you to express it that way, then all these other problems just go away naturally. But maybe that's writing the airline. I don't know.
Well, no,
I don't write an
has
airline.
plenty of its own problems. Well, you guys have adopted message passing is like the fashion of the day, right?
You can write procedural code in C++ or C#, and you can write, Erlang style code in C++ if you want to too. It probably takes different syntax, but realistically, right? We need the guidance to show up. We do need investments in the languages and the runtimes and in our tooling to help people. But it's not just a single approach.
Sure.
Right? It's not just a library, it's not just some language extensions, it's not just guidance. We need a single approach, and we likely need some time for the industry to evolve.
It's developing the patterns,
Yeah.
understanding the patterns, learning the patterns, and in fact, I think part of the evolution has to be education. And it's not just us learning what the right pattern is, we have to then teach that pattern. And by the way, it doesn't matter what language you're using.
That's true. If you were writing a program in concurrent Haskell, for example, shared state is sort of very, very well controlled. Side effects are very, very well understood up front. You're using monads to describe virtually all of the kind of state operations, whatnot. It's like you could use tools today that just are so foreign to our legion of developers that are imperative programmers. I don't care if you're C++ or C#. You're an imperative developer, and you've been trained to think in a certain way. And now all of a sudden, we can't just say, "Think different, man." So,
That sounds familiar.
but you know what? That's what I'm saying. The people are going to have to think differently, and you guys aren't going to be able to come up with a silver
We're
bullet.
going to have to say, think a little bit different at least.
Yeah.
But not that much. We want to give them a familiar surface, so at least it's not something totally foreign. It doesn't, as Stephen mentioned earlier, it doesn't totally borrow from a foreign set of style guidelines or coding guidelines. But we are going to have to ask people to think different in terms of how they design their program to begin with, because in some sense, in the last little while, we've abstracted things away from the hardware, the programming models away from the hardware. And in order to get the performance back from the new generation of hardware, we're going to have to take a step back. And people are going to have to be cognizant of the hardware they're running on in ways that we've asked them to forget. They're going to have to take a step back and say, "Oh, sorry, you shouldn't forget about cache locality. You shouldn't forget about the fact that there's multiple threads on your system, and they might be time slicing and switching between cores. You're going to have to remember that and think about that in the design of your program, at least for another couple generations, unless we come up with new abstractions that again allow us to teach them to forget that."
Well, actually, that is what we're trying to do, right? We're trying to give you abstractions that naturally you fall into. Well, I'm grouping together all these tasks that happen to be sharing the same state and happen to be, waiting together and things along those lines. And, if I do that, then I'm not really pounding on my cache. So you can think about it, and you and I have to think about it without question, right? But I would hope that at least the naive customer, if they follow our patterns and use our tools as we describe them, might accidentally just make it work very well. And then we have to provide them the tools, which we're not really talking about today, but I think it is an important subject.
Sure. We
have to provide the tools to discover that, I didn't do it right there. these two tasks are ping-ponging the caches across two different chips. Right? So
I think one of the important points there, we talk about, we've told people to forget about this sort of stuff. We've certainly told them that on the on the native side, but we've told them even more so on the managed side. You don't have to worry about the hardware, and that's, as Don said, at least for a little while, that's sort of not going to be the case anymore. Yeah, if you folks read Dr. Dobbs, Herb Sutter,
Absolutely.
architect on the C++ team, has a great column in there. And for the last few editions of that, he's been talking about sharing and how sharing is bad. If you read Joe Duffy's blog, and Herb talks mostly about native code. If you read Joe Duffy's blog, where he talks mostly about managed code, he's been echoing the same thing: sharing is bad, sharing is bad. And if the evidence that they cite in both his blog and in Herb's column actually comes back to some of the work we've been doing in our own performance tuning as we kind of work towards the release of both our native and managed work. And a lot of the major perf bottlenecks that we've had to remove from the system are based on just too much sharing, having to worry about, even on the managed side, where are things lining up on cache lines as we allocate the enumerators for p-link and so forth. And so, even for managed developers, for some time at least, this sort of stuff, knowing where things are and how things are executing on the hardware actually becomes an issue.
But it becomes unscalable when you have 1,000 cores, right? It doesn't, like you were saying, we said, concentrate on your business problems, concentrate on your algorithms, don't worry about the detritus that you have to deal with after objects are destructed, blah, blah, blah. So it's like now it's like we're going to say, well, wait a minute, the concurrency problem is here.
Yeah.
All right, freak out. Because,
But freak out, but only for a little while.
But only for a little while.
Hopefully by the time you're done freaking out, we'll have a better solution.
But look, if you had 1,000 cores to work with, then you could actually have machinery that could do a lot more things, like asynchronously. You could have a JIT that's always running, or it's not really being a JIT at that point, but you could have like a lot of things that haven't been thought of that could be targeting available resources, do a lot of very smart work.
Yeah, but
Whole program analysis.
I'm sorry.
Yes.
Ironically, when you get to 1,000 chips, the sharing problem just gets multiplied. So all these things that we're asking you to worry about for a few more years, if you ever to get a 1,000 core machine to work on in the next couple of years, be very concerned about sharing, because the sharing problem just gets multiplied the more cores and the more contention you throw at it.
I'd add on to that, say, if you get a 1,000 core machine in the next few years, let us know.
Yeah.
We'd love to test on it.
Sure.
We don't have one of those right now.
Sure. That's just like the kind of crazy example. But if you look at the way, like transistors, the way of the transistor,
Of course, sure.
at some point we won't be laughing at that.
No.
And we'll, I'll have more gray hair. We'll probably have a little more gray hair, but we'll still be healthy
Less.
and very.
Don and I will have less.
I'll have
right?
less.
But we'll still be healthy, man.
Yeah.
We won't be kind of like running into walls and mumbling. So it'll be sooner than later. So let's continue this conversation. And I guess I'm looking at you because,
He sits in the middle.
he sits in the middle.
I chose the wrong seat.
You chose the wrong seat. You never know. Actually, that could be a fun new interview style. And then have it automated. You don't know where it's going. So
it might be interesting to get back to some of the actual differences that we've had to deal with between managed and native. Trying to think of one. So a good example, Rick briefly touched on templates earlier. And if you look at I'll take a very simple example, but the design for our parallel loops. We've got parallel for in both managed and native. But if you look at the way that they're expressed, for managed, we've got parallel.for, and we have overloads for int and long. So you can do int32 and int64. For native, it's just a template where you basically can specify any kind of integral or...
There's a set of operators that you need to support, and as long as it looks like an integer, essentially, meaning that you can take a modulo with it and you can
Add and subtract.
Yes,
Do the
standard
math.
stuff. Then it'll just compile and work.
Okay.
And that's really exciting. But it's not something. It's not like we didn't want to do it in the managed space. It's just harder.
With generics in .NET, you can't basically. There's no way to currently express operators on generic types. So there's no way for us to say we want to constrain T to be something that has plus and modulo and whatever else. So we end up providing concrete overloads for int and long. We could have defined a new interface, an iArithmetic interface, and made sure that all of the basic types implemented this, but then we'd be making virtual function calls or whatever it may be, or interface calls every time we wanted to do an add or a divide, and that starts getting very, very expensive. And you probably also at that point start needing to worry about more concurrency issues as you do these sorts of operations. So that's I think it's an example where they look similar, but there's actually differences in these APIs we've had to deal with based on the support that the platform provides.
One of the things that's nice about Manage is you'll get a really readable error message with Parallel.4 if you pass it the wrong type. If you pass the wrong type to Parallel 4 in native, you'll get a nice cryptic template error message. And this is something that'll get better in the future as concepts come out, because we can say it requires operator equal and it requires it to be modulo or whatever because that's one of the things that it allows. And so that'll actually be something that helps, and we won't have to do virtual function calls, which will be cool too. A place where we're similar is with parallel for each, right? Where we have a different construct in native. We say pass it in a pair of iterators, and in Manage we say give it an enumerable. But the spirit of that is very, very much the same, and you really can, I believe, have pretty much any enumerable pass it to it, and as long as it's thread safe, just like as long as you pass a thread safe iterator to our native version, we'll support it. And I think that's wonderful that it translated so well there.
There are areas where we could have made the same decision for both, and we ended up not for a variety of reasons. One particular example that is sort of forefront of my mind is an exception handling. So in our parallel loops for Manage, we've decided that it's most important to ensure that no exceptions get lost, that if an exception gets thrown, you can sit around and sort of take the time to wait for all the exceptions to be gathered up and then throw the aggregate. And on the native side, we end up throwing the first rather than throwing them all. Both models provide a mechanism for sort of implementing the other. So in Manage, once we got aggregated all of them up, we could just pick one of them and throw it. And on native, we could use try catch and basically catch all of them, store them, and then rethrow them. But the default is in effect different. And I think Don and Rick can probably speak to why we opted for that solution in native.
Yeah, well, I think the biggest problem is just what Stephen noted. In .NET, exceptions are easily inspectable, even when they get marshaled across a thread boundary. They're still, derived from system.exception. You can still downcast them to my exception and inspect them very easily. That's just not the case in C++. When an exception gets marshaled over, we use something new in C++ OX called exception putter. And basically that turns an exception into an opaque blob. And the only way to inspect it after that is to rethrow it, which is not a very performant thing to do in any kind of programming model. So we took the approach that an exception is, it's usually something that would crash your process, so you should let it crash your process, especially if it's one of these low-level access violation things where you make no attempt to catch those or marshal those, they'll crash your process.
Okay.
And if you're using exceptions in a parallel for, you should throw one, and we will marshal that one over and rethrow it on the waiting thread.
The other thing I'll say is you probably will see blog posts and things like that from us saying, here's how to get something that looks like an aggregate exception or all the exceptions, so that you can actually, if that's what you want to do, we can at least guide you there so it isn't very hard for you to get there. Because we know it's important. We know that there's a whole set of users that want this.
So I guess one of the things I think would be fun to talk about, where we can, is sort of, what's like on the native side, like what's the biggest problem you guys are dealing with right now in your conceptual framework of solving a problem, or even a technical problem? I mean, it's nice to talk about the solutions that we've worked on, and that's awesome and brilliant stuff, but what are some of the hard problems that you have facing you that kind of keep you awake at night?
I think the answer to that is not specific to native or managed. I still say that you have a lot of tools that allow you to inject parallelism, but they are fundamentally unsafe. So unless you know what you're doing, and unless you take steps to protect yourself, you're going to have hard to debug errors. And we're still just scratching the surface on how to add safety on top of the performance that we're allowing you to add. We're still scratching the surface on that. We don't know where we're going to go. We're going to get part of the way there in Dev 10 with the solid debugger and performance analyzer, but there's a long way to go there.
And you've seen some of the incubation efforts we have. You've previously talked with Dana about our efforts in software transactional memory.
Absolutely.
You've talked with Nicholas and Josh about Maestro. And,
Yep.
and a lot of the concepts from these do cross boundaries between managed and native. Those two incubations happen to be based on managed. I think if you were to ask pretty much anyone in our product unit, what the one thing is that keeps them up at night, it is shared state.
Yeah.
And how do you provide safety?
It doesn't matter what
You could almost pick any of us in the hall and ask us when we say shared state, because we're going out of our way to make sure that it's relatively straightforward to express concurrency, and that a lot of the time it'll scale really, really well, and hopefully when you're careful it'll scale wonderfully. Right. So if those are the three pain points: shared state, expression, and actually getting code to scale, we're making really good progress
on the latter two.
On the latter two, and shared state is still really hard.
I mean, the best progress we've made in shared state is giving us tools to make sure there's no shared state, right? And limit the areas where we're shared state.
Yeah, and Dev 10 on the native side, we're offering an alternative to shared state with message passing.
Mhm.
That's our official answer.
But
it's
with,
still hard. But even there, you have to be careful.
Right. Yeah, it's the same thing. We can have something like the CCR
Yes.
managed code, right? Which is in concept very similar to what we have for asynchronous agents in native. And in both cases, while I can say we're based on message passing, we can pass structs around, or we can pass blobs of data around that get marshaled by value rather than by reference. But I could still sneak in some references on the managed side or some pointers on the native side and end up sharing things that we didn't intend to share.
Well, and I think the least that's going to happen, of all the possible things that can go wrong, the least bad thing is that you'll see bad performance if you have shared state. It's
At least it's still correct.
Yeah, at least it's still correct, but you're almost guaranteed to see some performance loss if you have shared state, because it's a source of contention.
Yep.
But in the context of the problem, that's relatively unacceptable, because it's all about scaling to increase performance and
Right.
the speed at which computations can.
Right, and those other things like deadlocks and races and hard to reproduce races that only show up on some guy's box out in the field the day after we release.
Yeah. In fact,
Who happens to have
Agreed.
1,000
That's a
cores.
good point.
Yeah.
Yes, he built it himself
He built
in his
himself.
backyard.
There's one person on our team that recently actually told me that the number one thing that keeps him up at night isn't shared state. It's exactly the problem that Rick just mentioned. Rahul, who's our test lead, you actually talked with
Yes,
him
a couple times.
about concurrency testing. So
Yeah,
he's
yeah.
our native concurrency test lead, our native test lead. And the thing that keeps him up at night is these cases where he'll see something repro once in 1,000 times on a particular architecture with a particular number of cores and nowhere else. We have a giant lab that's running tests constantly on every kind of hardware you can imagine you can actually purchase today with different operating systems, different number of cores, different cache layouts, and whatever it may be. And this repro is just in this one particular case consistently, but on this one particular machine. And he says, how can we deal with that? How can you live in a world where that can be?
We should probably take a tour there sometime. I think that would be
Sure.
really. I
That'd
think
be fun.
Niners
That'd
would
be
love
fun.
to see that, and then just kind of explain to us what we're looking at
You
each
could have
test.
headset mics and these bubbles.
Yeah.
Actually hear us.
That would be cool.
Yes.
Excellent. I mean, I kind of, George, is really interesting in the sense the way he thinks about concurrency. At least the last time I talked to him, really wasn't thinking about concurrency.
Coordination.
It's coordination, and I think that's an interesting way of looking at the problem, especially in the context of state. Right, when you're coordinating. I mean, I think it's just an interesting model. CCR is not certainly the end all. It's not the silver bullet.
None of the models we're working on are.
Exactly. But Joe made a good point in our last talk about linear types and the notion of putting all these pieces together, so that if you could say this type can never be modified, I promise I'm never going to change anything on it, and no one else can screw with it.
Right.
That's one way of guaranteeing.
Purity is beautiful.
Purity is a good thing.
Beautiful. But let's say, here's a great example. still of how you shoot yourself. And I think Rick wrote an article, which hopefully we'll see soon, where he was doing dining philosophers, and in one case he had a greedy algorithm, and in one case and it deadlocked, right?
Yeah, the
and
philosophers were greedy.
Yeah, the philosophers were greedy, and so in this case he has philosophers that have two chopsticks, right? And so the dining philosopher's problem is that you think and you eat. Okay, and when you want to eat, you need to grab both chopsticks, except the person who put out all the utensils only put one chopstick between each philosopher on this round table. So there's a bit of contention here trying to get both chopsticks. And if you're greedy and you grab one and then you grab the other and never let go of this first one, well, you can get, you run once and you immediately are deadlocked, right, if you're greedy. So you have to use a non-greedy algorithm. So we've given you the ability to specify either greedy or non-greedy algorithms. And so even here in this environment where we're doing everything with messages and we're passing things along, we get into a deadlock.
Well, and the other interesting thing about that is it's a two-phase commit join, which
Yes.
sounds an awful lot like a transaction.
Well, yes, two-phase commit would imply transactions.
And so if a join is take a series of message blocks that you're going to get messages from, and you can join and wait for them all to fire. You can either do it greedily, which, as Dana explained, you take it as soon as you get an offer of a message, or you wait for offers for everything, check all the offers to ensure they're valid, and then take the messages, which is how we did this.
Or to put it differently, when you discover you couldn't get the second one, you put it back down again,
That works,
right?
yeah.
Which is the re-execution loop that we do in transactional memory.
It's very similar. I've been thinking of a lot of this stuff as Venn diagrams. It's like, okay, let me circle around the pieces of these Venn diagrams where we're actually solving them in the different technologies across our managed and native stacks.
Mm-hmm.
But all the problems and all of the solutions are actually, a lot of them are very similar, if not the same. It's just how they surface.
I actually think what's something we haven't talked on. We've talked about tools in sort of in the abstract sense, but to Rick's point, I think one of the places where you can really see that we're approaching problems from a similar point of view is in our tooling, our Visual Studio tooling that we're doing as part of Visual Studio 2010. Unfortunately, no one from our tools team is here represented, but I think you've talked with Daniel Moff,
Absolutely.
and Sean Norberg, and the tools that they're doing.
Steve
Tashira.
Yeah.
The tools they're doing for Visual Studio 2010 are universal across both managed and native. You get the same support regardless of what you're using. If you're using a parallel loop, you see the parallel loop demarcated on the profiler. If you're using tasks, you see the task view. You get to see your parallel stacks view showing all of your tasks and how they relate to each other, and that's regardless of whether you're using managed or native.
If you're in the parallel profiler and you see a problem, the problem's going to look the same.
Yep.
If I'm looking at the parallel profiler and I see a lock in a parallel 4, which, by the way, you can just see that there's a lock in there, and it looks the same, no matter.
It looks very red.
It looks very well. Not only does it look very red, it looks very serial, right? It looks like a staggered line chart where you just take your nice serial portion and you've just split it across threads. It looks the same, whether you're looking at it in managed or native, or in our abstractions, or in just Win32 threads. And I think that's wonderful because it allows you to actually learn something once and apply it to whatever you're doing, whatever language or platform you're working on.
So it really gets down to the point of use the language that's correct for your problem. The tools you have are familiar across all the platforms, and so all you're now doing is just picking the best tool for your problem, which isn't that what we're trying to do? I mean, that is what we're trying to do. Just and whether now your problem is solving your business problem in a highly concurrent world. So we're giving you the tools for the concurrency, but it doesn't matter about the language. So Haskell and Herlag people will argue with me. It does matter about the language.
Well, it seems
argue
like
with me
C
anyway.
people would argue. Because it seems like for you guys, and this is just saying in the sense that if you're a systems programmer and you program in C++ every day of the week, right, or C, whatever, you're writing drivers, you are really close to the machine. You already, when you map out a solution to a problem, you're already thinking about very low-level things, and it maps up itself very, very relatively close. You're not writing assembly, it's very close to what you're doing to some degree. So when you add these new things like learn about this and think about not doing this type of thing such that you don't create locks and blah, 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 I think that class of developer will have an easier time conceptualizing what we're asking them to conceptualize, whereas somebody who we train to say, hey, you don't have to think about memory, man. You just go ahead and do what you need to do. Throw up a new object, add some functionality to it, rock and roll, man.
But I think at the same time, you will see that sort of manifested in the APIs that are being provided. If you look on the native side, for example, you have the option of choosing whether you want a task group or a structured task group. When you create the scheduler, you have a whole slew of policies that you can specify about how the scheduler executes. The kinds of things that a developer who's pedal to the metal all day long, been doing C or C++ for since they were 2 years old or whatever it may be, because those developers have been at it since
well,
they were 2 years
game
old.
developers, man, there's a lot of them out there.
So those options are being provided. If you look at the APIs that are being provided for managed, while a lot under the covers, a lot of the functionality is the same. The same sort of tweaks and knobs aren't necessarily exposed. So we don't have the difference between a task group and a structured task group. We don't want managed developers necessarily to have to think about that sort of thing, because if you look at the rest of the .NET framework, a lot of that has already been abstracted away. For example, if you look at like the collection types in the .NET framework, there are many different ways to implement a dictionary. There are many different ways to implement a queue. And if you look at something like Java, for example, you'll have sort of a base dictionary interface or a map interface, and then you'll have the hash map and the skip list map and every different type of map, and it's all concrete classes represented. And the developer has to go and choose which of those they want based on the performance characteristics, very fine-tuning, micro-optimization, and so forth. You look at what we have in managed in the .NET framework, and it's just dictionary. And we sort of go under the assumption that this is good enough for the 99% case, and if someone really cares and knows that they actually need something slightly different, they can go find it from a third-party vendor, they can write it themselves, and so forth. And I think to some extent, we're following those same principles in what we've done in our managed solutions, where if you look at the native solutions, there is a little bit more tuning that can be applied.
Sure.
Yeah, but to talk about the dictionary does work in 99% of the cases.
Absolutely.
It's a great dictionary, and you guys have a lot of folks and customers you're talking to that are doing high performance computing.
Absolutely.
With this, and I'm talking serious number crunching where performance matters a lot, and they're being successful with it.
Yeah.
So don't talk about the lack of knobs to
right,
mean that it's
not necessarily a bad thing.
Yeah.
Right? It's trade-offs. And if going back to one of Dana's comments about sort of the language doesn't matter. Obviously, there are scenarios where people choose a language for a given set of traits, right? You may choose C++ because you want that extra 15 or 20% perf gain that it provides over the kind of maybe the equivalent managed solution. You may choose managed if you need really productive development and you don't care as much about the performance, but you still want performance gains, you still want the benefits of parallelism and so forth. Mm-hmm. I was talking with one customer in the race car industry. And their big problem is they have a lot of number crunching to do. They have race cars going at week races every couple weeks. They've got a lot of telemetry data and things to process between races. They definitely care about performance and number crunching and so forth, but they also only have 2 weeks to turn around the next version of the application for the next race, and it's much easier for them to make those sort of modifications. It's better for their business to do it in managed code, and for that particular case, they can take the 15 or 20% or whatever it may be difference between the managed and native solution. There are other customers that will be running some algorithm for weeks on end. They don't need necessarily that level of productivity, or they have an experienced development staff that is very knowledgeable in C++ and is able to make these changes rapidly. And they may opt for that extra 10% or whatever it may be performance gain that you would get from native code. And then, of course, there's just sort of the what does the company's staff know? What do they use? What do those folks who are working on a particular problem, what language are they most experienced with? I think our ultimate goal is that, and I think this was Dana's point, is we're providing basically the same set of solutions for both managed and native. And you can choose whichever one you want for your given problem, and the basic facilities will be there to do parallelism.
Great.
And so it's up to you, and it's up to your business, it's up to your business choices. You might have to learn something new, and actually I want to say through the tools is where you're going to be learning something new. It's not because of what I give you in the way of a language bindings. I mean, yeah, okay, so P-Link, I might have to learn some nuances about that, or I combinable object for C++. These are these are kind of one-off learning, but the real systemic learning is going to be when I take a look at the performance analysis tool and I go, oh, I know what that pattern means. Where is this in my program? And it doesn't matter, by the way, if I'm looking at a C# program or a C++ program. I'm looking for the same thing. I might be looking for lock, okay, or I'm looking for some sort of shared state, and maybe that shared state, oh, I did an allocation here.
Yeah, and
That's what it is.
And that's where it starts. It starts in deep analysis, but it moves from analysis through to guidance, through to best patterns and practices, so that we all get better in the industry at doing things which, don't have bugs, aren't slow, right? Because we know how to build. Oh, well, that's this kind of problem, and the general way to approach this problem is with this solution. We learn, we agree, and we learn, I think, collectively what are the good solutions, and we apply them. We're still really early in this. There's been a lot of research for a long time that we get a draw from. Fortunately,
There's still research going on.
and there's still research going on, but it hasn't sort of hit the mainstream developer industry yet.
We were talking to one of the Gang of Four recently, and he was talking about coming up with new patterns for parallelism, and that there's actually a whole effort going on right now to push developing parallel patterns and writing them down. And I assume we'll get a whole new book out of this, Gang of something or other. Maybe it's a Gang of Thousands book, but we're gonna need a new gang book of parallel patterns. There's been some early books on parallel patterns, but I don't think they're very complete now. I think we're just beginning to see the beginnings of parallel patterns and what that really means. And then, undoubtedly, as we learn, we'll reflect that in our languages, reflect that in our toolkits, reflect that in our libraries, and we'll reflect that in our education.
Excellent. Well, on that note, thank you guys, man. Always great to come here.
Thanks for
Chat.
coming. We appreciate it
very
very
much.
much.
Thanks, Charles.
Keep up the great job.
You've been
guys.
making the trip over here a lot, so
I
Thanks a lot.
have, man. It's a good building.
Okay.
Thanks.
Take care.